Make sure you fill up the attendance link, your attendance through the link. Let's continue with our lesson. Um, the other day we stopped at activity 2.24. You can hear me loud and clear, right?
Yes.
Great.
Yes.
Thank you, Fatima Aizat. Okay, all right. So we'll continue with this activity here. I'm going to increase a bit. Okay. Okay. Now, let's continue. The other day I said for the rest of the activity, I'm going to um, just go through it. Because there are actually similarities between the next couple of, I think there are almost similar activities, three of them. I'll just go through, I'll explain it. Of course, at the end of this chapter, I'm going to share the slide with, complete with the answer with you. I'm going to update it in the author. All right. Now let's go through it. Last class, we have already proved, for rectangular, for trapezoidal section, for a given characteristics, right, you'll get the most efficient, uh, the best section lah, basically. Did I admit it already? Okay. All right. Now, okay. The most efficient section. Okay. Um, I have to admit, one by one of you. Okay. I hope no one is coming in, uh, anymore. All right. Um, Now let's look at this. We have let's look at the question first. It says slightly rough brick line. Okay. Now from the description of, just a second, someone is coming in. Okay. All right. It says slightly rough. It says slightly rough brick line channel. So it the question already give us the description of the channel lining, which is rough brick. Right, slightly rough. Okay. Now, if we go to the table of roughness coefficient, what you could do, try to find where you have this lining of brick. If you look at this table, right, at the last line there, you have brick. Now, the Manning roughness coefficient is given in the range of 0.014 to 0.017. Now, what you could do is, when you are answering this question, right, you could say for rough channel, you are going to choose the highest limit of the roughness, which is 0.017, because you are assuming it to be very rough. When it's rough and when you choose higher Manning, it actually will reduce your velocity. Uh, Velocity of the flow or the rate of discharge lah, basically. So you have justified that since the question say the lining is rough, that's why you choose the higher limit. It doesn't matter. Well, you could also justify if you are using the slightly lower Manning, maybe 0.015. You could say, well, the question say it's slightly rough. It doesn't matter. You can choose any number, but you normally will provide justification why we choose a certain value. Now, let's go back to the question. So now what I'm choosing is, I said it's rough brick line. Then I'm using Manning roughness and 0.017. Correct. Um, now, okay, I think I should just use without the PowerPoint slideshow. Okay. Okay, now, um, if you look at here, what is given is, the discharge is provided 25 cubic, and then the longitudinal slope is provided as 0.4 times 10 to the minus of 4. All right, it's very mild slope, and then the question asks you to right. The question asks you to find it says it's not very direct. It doesn't say, well, it does the question doesn't ask you to specify what is the channel's width, the channel slope, side slope, and things like that. It will just, if you look at the question, right, it will just say analyze the proportions for an effective trapezoidal channel section. Now there are two parts of question here. The first part, it says it actually stated the side slope, which is given as 1.5 horizontal and 1 vertical. Now, if it's given, that means you cannot change your side slope. You have to use this side slope. Therefore, the side slope is constant. Well, the second part, it says it doesn't give side slope. It just says find the most efficient or analyze the proportion for the most efficient channel section of trapezoidal shape. So what you are going to do is you are given the choice to choose any side slope. Well, of course, we are going to choose the most efficient side slope, which is z equals to 1 over square root 3. Last week we have showed, right, or last Sunday we have showed that the most efficient side slope would be 1 over square root 3. Z equals to 1 over square root 3. Now, the question asks us to find, basically the dimension of the trapezoidal channel. Now, if you have a trapezoidal channel, what are the dimensions that you need to provide? Of course, the bottom width, B, the side slope, which is Z. What is Z? And then the depth of flow, because the effective depth of flow, since discharge is provided, longitudinal slope is provided, therefore you can find Y, right? So let's start to answer the first or solve the first part of the question. Now, side slope is provided. So remember that we have that table, right, which is the formula. Which one? This is the one, the bottom one, the best hydraulic section. So if you look at the trapezoidal, side slope is 1 over square root 3. Now the first part of the question already give a constant side slope, which is not 1 over square root 3. So you cannot use this formula for area and also wetted perimeter, because the formula for area and wetted perimeter is when you are substituting the z equals to 1 over square root 3. But remember, we have showed that, well, even though the side slope is is constant with whatever number, you can still prove that the hydraulic radius is y over 2, or half of y. Okay, we still can use this. Let's go back to the question and see how we solve it. Okay, now for fixed side slope, okay, z equals to 1.5. So remember, if you cannot remember this formula, I think you should know the step to get this formula, which is very simple and direct. That means you write A in terms of, you write the flow area for trapezoidal formula. You rearrange your formula where you make B as the subject of the formula. Then you substitute the B in the wetted parameter formula. Then you differentiate P with respect of Y, set dP over dy equals to 0, then you'll get this formula here. And of course, R is still half of Y. Now, since I'm using this formula for best, most efficient section, if you look at here, my depth of flow, there's a subscript E, which stands for most effective or efficient. All right, depth. So I substitute Z, which is 1.5 in this formula. So therefore, my A is 2.106 y squared. Now from the Manning equation, right? Okay, I substitute. I can actually write this in terms of section factor. All right, where I have my AR to the power of 2/3 on one side, or become the subject of the formula. Then I substitute all the known values, right? Okay, given values. Then I straight away. This is a straightforward question. I'll get my y equals to 2.830 meter. Then of course you have already have your y, you have your z already. What else? You know the basic dimension that you need would be the bottom width. So remember here your formula for your flow area is this guy here. Again, if you want to get to this formula here, you actually rearrange the flow area formula to become this, right? Where you make b as the subject of the formula, right? So now this expression here is actually your A, which you have already substituted your Z equals to 1.5. So you simplify it, you become 2.106y minus 1.5y. So you are going to have 0.606y. Then substitute y, which is 2.83. Therefore, your bottom width will be 1.714 meter. All right. Now, you have already solved the first part of the question. Now, the second part of the question where, Z is not fixed, it's not given. So they allow you to choose the best Z or the side slope. So you have showed, last Sunday you have showed that the best Z would be when it is equal to 1 over square root 3, or when you solve this, it will give us 0.5774. And also, you can actually plug this formula out of the table where your A is square root 3 y squared. Of course, you have already substituted z equals to 1 over square root 3. And also your hydraulic radius is y over 2. Now, why did I use this 2? Because I know that these 2 are required or needed in the Manning flow resistance equation. So therefore, either you substitute directly, or you can rearrange this in terms of section factor. Okay, you also get, you can solve for your most effective depth of flow, which is 3.045. Now, why do we need y? Of course, when we want to construct the best or most efficient section, right, we need to know what is the depth of the channel. Of course, we are not going to build exactly as the depth of flow, all right? We are, of course, are going to allow some free board so that it won't overflow, right? So we are going to extend it, all right? Increase the depth of the channel. So you at least once you know the depth of flow is 3.045, okay, you can have some free board lah. Okay, it depends on how much free board you want to provide. Then of course the next variable would be the bottom width, the channel's bottom width. This is actually plucked out from the table as well. Okay, so B is 2 over square root 3 YE. You substitute YE, you are going to have your bottom width equal to 3.516. Okay, this is the most efficient side slope lah, 1 over square root 3. So far, guys, do you have any question? Girls and guys, do you have any questions so far? Quite straightforward, right? Any question? No one.
Okay, doctor.
Okay, yeah. All right. Thank you. Thank you. All right. Now, um, let's look at this activity 2.25. The concept is the same. If you look at here, there are two parts. The first part is when the side slope is constant. Okay, I'm just giving you more exercises so that you can practice it on your own. Okay, the second part is, where side slope is not given or it's allowed to change. So you, of course, we are going to choose the best side slope. Z equals to 1 over square root 3. And then if you look at here, again, the question give you the type of channels lining. It is gravelly earth trapezoidal channel. So in this case, okay, if I refer to table 2.1c is earth channel, okay, and then it has gravel. This is the guy, the third part, which the range of Manning roughness is between 0.02 and 0.03. Now this time I chose to use the average value. So I sum them up. Okay, so I take the middle value, which is 0.026. Okay, so I'm using this Manning value for both cases. So,
Doctor,
yes.
if you the maximum 0.03 also can, right?
Oh, yes, yes, yes. You can use 0.03. Correct. Of course, sometimes like earlier, right, in activity 2.24, I asked you to justify why you want to use 0.03, right? For
Yes.
example, it's rough brick lining. It's, it says rough, right? Because the table give you brick lining is there's a range, right? So when it says it's rough, of course we are going to use the higher value of Manning roughness, right? Okay. So okay,
Okay.
okay, great, thank you. So you can justify lah. All right. So maybe in this case, right, you'll say taking the average Manning roughness. So you show you are using the average value, right? So I mean actually here, if you look at it here, I'm using the average lah. Okay. Thank you, for asking the question. Of course, when you are using variable Manning roughness, your answer among yourself, you are not going to get the same answer, but we have the set. That means, of course, we have, if we are using 0.022, what is the answer? We have it. Okay, it's very easy for us lah to use Excel to get the answer, all right? Because you have to do it manually, all right, on paper. Now, I of course I have the solution here. It's the same step, so I won't go, go through it again. I'll share this with you. It's best, hydraulic you can easily score. However, you need to do practice. Okay, for example, if you are combining this, right, why you get, the power becomes 8 over 3, you have to try it on your own, then okay, that this is 3 over 3, which is to the power of 1. Okay, you add this guy, and then that's why you get 8 over 3. Okay, um, no, no. Let me go through it again. It's actually y to the power 8 over 3. So this would be y to the power of 6 over 3 plus times y to the power of 2 over 3. So therefore you get 8 over 3. Things like that, right? So you have to try it on your own, then you know that, look at this, you don't even have to solve for try and error. If you don't try it, okay, I have cases when students don't try it out even to solve this equation. Okay, uh, even to just solve the equation, they use the calculator to, try to key in the form expression and then press solve. No, you don't need. You can actually simplify it to become this and get the answer directly. Unless you try it, you won't know. Okay. Of course, again, even for, rectangular, if there's question on rectangular, right, I would need you to find the bottom width, all right? For if the question asks you to find the most efficient section, you don't need to find Z because of course Z is 0. You need to give me B, uh, BE lah, okay, and YE. For triangular case, therefore you need to give me, Z, okay, and also Y. All right. I hope we are clear. Of course, either Z, E. It depends. Normally you need to find ZE lah, and also YE. All right. Okay, you have that. Typically, these are these basic sections that we will ask you. Okay, this is the second part where you use z equals to 1 over square root 3. So the same process here, okay, same process. Then you get this. Try it out so you know where to look at. Where's the formula to look at in the table? All right. It's the same again, similar question. Okay, but this time the question has provided the Manning roughness coefficient, so it will be simpler for you. Okay, I'm just going to run through. All right. If you have any questions, stop me. Okay. Now, okay, this is actually a revision question. Okay, if you look at this question actually came out in the final exam paper, um, which is almost a decade ago lah. Okay, all right, less than a decade ago. Now, well, the concept of hydraulic is for drainage design. Uh, doesn't change much. It remains the same. So even when the reference book that we are using, Wendy Chow, that was dated more than how many decades ago, right? But you still, if you go through that reference book, you'll find wonders, right? There are so much of knowledge. um, Even when I read, when I read it the second time, third time, I always find new knowledge. The understanding is much different already. Okay, it's deeper. All right. It is good if you can uh, reread books, especially books like Wendy Chow. Of course, every time you read it, you'll find new knowledge. Now, in this question, it asks you to find the normal depth. Okay, of course, you are using the section vector formula. That means you're Manning, but rewrite it in terms of section factor. And this time, you need to use graphical method. Try this out. That means you have to have, tables, and then coordinates of y, and also the value of AR to the power of 2/3. Okay. Uh, Provide couple of values where uh, your this AR to the power of 2/3 value falls within these points here. Then you need to draw graph. Okay. Graph of y and AR to the power of 2/3. Then uh, you need to find, I don't know how it looks like. For example, you have points, right? You have points. Then, based on the AR to the power of two-third value, you can actually find your y naught. All right. Now, try this out. Okay. You need to find what is the y. Okay, in this case, of course, in my case, right, what I'll do is, you look at this. This is the Q given. I will still try to find what is my Q here. All right. Of course, if my Y increases, my Q will increase as well. But I don't know whether this portion here is less than 63.5 or more than 63.5 Qmax. So if it's less than 63.5, you know that the depth will exceed this trapezoidal section here. It will, be in, it will actually be in the rectangular section as well. So what I did is, I said I'll check for Q1 first, which is this section, the trapezoidal section. So when I check, all right, my discharge for Q1 is 48.17, which is 63.5. Now I know that, my Y naught will exceed 3 meter. Okay, maybe slightly lah, a bit. Okay, because I have accidents of more than 10 QMAC. So therefore, okay, I know my Y1, but I need to find Y2 so that I can get my Y naught, which is Y1 plus Y2 lah. All right. Now, therefore, if you look at here, I already found out what is my Q for trapezoidal section. For actually, we tried this out before, all right, in one of questions. So I just go through this very fast. For compound section, right? So since I know that my Q, my discharge actually cover this compound, the both sections, right? So I have my flow area for the compound section. That means A1 and A2. I know my Y1. So if you look at here, I actually substituted my Y1, but I don't know my Y2. So my expression of flow area is in the unknown of Y2 only. The same thing for weighted parameter. You know that why you need to find A and P is because you want to substitute this in the Manning formula, Manning roughness or Manning flow resistance equation. You need to solve for A and R. The other variables are provided, like Q, S naught, and Manning are all provided. So you have to write this out. So once you have written this out, you know that the only unknown will be Y2. All right. Therefore, you can actually directly you can solve Y2. All right. Once you substitute in the Manning flow resistance equation. So same thing here. I substitute Z1 and Y1. All right. So the expression of weighted parameter is 14.82 plus 2Y2. Again, if I'm too fast or if you have question, you can stop me. Um, Now, uh, okay. Um, just a second. I need to switch off this. Okay. Now, um, this is Manning roughness flow equation. I rearrange this in terms of section factor. If you look at here, I substitute my flow area and weather parameter. So therefore, this is not straightforward. So you have to use try and error method, either using your calculator or manually. You can solve for y2. So try and error gives y2 equals to 0.4037. Therefore, the the depth of uniform flow is 3.404, which is y1 plus y2. Y1 is 3 meter, okay, which is provided. So now,
Doctor,
yes,
but just now the question asked us to use the graphical method, so we need to use the graphical method.
correct, correct. You can try this out, graphical method. You are right. This is where I explain how you need to show this actually. Uh, You're
Okay.
right. Thanks a lot. Okay. Thank you. Yeah. Of course, if you are using this method, I'm going to deduct some marks. Basically, try it out. Draw the graph. You'll get something. A value of something like this. The rest are the same. All right. The rest are the same except up to here. From up to here, you need to use graphical method already. You cannot use try and error. Okay,
Okay.
all right. Thank you. Thank you for asking. I also it slipped my mind too. All right, it says graphical, but I have try and error here. I forgot to remind you. So up to here, this is very simple. No, sometimes we would like to check our answer. All right, I guess using calculator, if you are practice quite a lot, right? Quite a number of practice done using calculator to solve this. You can actually do it very fast to check your answer via whether your graphical method is correct or not. Okay. Okay, now the last subtopic, okay, would be about channels of compound section. Oh, this may involve, we have, this is a compound section, but who knows, right? Maybe this part, the bottom part, which is the trapezoidal part, I may use concrete lining, and this, I may use uh, rocks, okay, as lining. So the roughness coefficient would not be the same for these two parts. Now, how are we going to find it? You can actually use this formula here. Okay, if it's the same, it's simple. Okay, if it's the same, you can just choose one formula. If it's different, then what you can use is you need to find Q. This is actually the formula here is basically the total Q for the whole channel would be Q1. If there are two separate sections, you have Q1 plus Q2. If there are three separate subsections, you have Q1 plus Q2 plus Q3. That means you have to find Q for each subsection, because each subsection have different roughness coefficient, so you have to solve for that roughness coefficient. If you have, if you find the total A, you can't actually find, substitute the various roughness coefficient in one formula. So you have to solve for Q1, Q2. If there are three, then solve for Q3. If there are n section, then you have to solve for n number lah of Q. Then you add them up together, you'll find total Q of that whole compound channel. Now this is just the rewrite. This K, I hope K would be Q over S naught. All right. To the power of half lah. You'll come back to velocity if you have in this case. Okay. Either one lah. Okay, let's take a look at one example here. I have activity 2.28. This will be our last activity for today. However, later I have an exercise for you to do. I don't mind, if you have discussion. However, I really want you to, try it on your own. Okay, but before that, I would like to, go through activity 2.28. So in this chapter 2, we have as many as 28 activities already. That is quite a number. Okay. If you look at this as a cross section of a river. Okay, the longitudinal slope is 0.009, Manning roughness is 0.023. Okay, in this activity here, there will only exist one Manning roughness coefficient. So you can actually find, combine A and also combine the P, because there's no effect on the roughness. There's only one. So it's the same. That means you can actually factor the Manning. You'll get the same if you combine it too. So try this out. Okay, I'm giving it. I'm sharing the answer soon with you. If not today, maybe tomorrow. I'll upload the notes for chapter 2. It's the same. I find A. If you look at here, I have subsection 1, subsection 2, subsection 3. I don't mind, okay, if you want to have more than 3 subsection, you may have 1, 2, 3, 4, 5. It doesn't matter. But for me, the least numbers of subsection is simpler lah. I don't have to find so many of it. Okay, so I'm using 3 here. Okay, so I find total A, I find total P, then I find my Q. Since my Manning roughness only one value. Okay, let's take a look at next case. I thought that would be the last. No, there are 29. Okay, now in this case, I have subsection 1, 2, 3. Look at this. Manning roughness varies between subsection. Subsection 1 and 2, they have the same Manning roughness, but not subsection 2. Okay, if you look at this may have more erosion lah, all right, compared to this. This may have more vegetation on the flood plain. Normally, this is the flood plain, huh? Okay, when there's overflowing, okay, this area will be flooded. Therefore, it's called flood plain. So you have more. It's more rough. You have more roughness, on the flood plain as compared to the main channel. The main channel, you have roughness of 0.02. Now, how are we going to use the formula? Remember the addition of Q for each subsection. So let's look at here. For varying Q, remember I'm using the summation of Q1, Q2, Q3. I have three subsections, right? So therefore Q1, Q2, Q3. I need to find discharge for each Q. All right? Okay, now Q1. Let's go through one by one. Look at this. For Q1, for subsection 1, the weather parameter will be this one here. Okay, if you look at here, this guy here. All right. Now, BA, okay, 2, YA 1 plus Z. Okay, you need to check this. Try to check this whether it's correct or not. Okay, but I think I know what I'm doing lah. Okay, just a second. BY. How come it's supposed to be the same? But it's okay. You check my answer whether it's correct or not. Y 55. B. Oh, this is section 2. Okay, no wonder. This is subsection 2. All right, I forgot. Okay. 3. Okay. You try it on your own. Check my answer whether it's correct or not. Okay. This is the one. Okay. A1 and P1. Okay. So P1 will be here. A1, of course, is the flow area. Now for subsection 2, P2 would be this one here. Okay. Make sure you don't go and add this up. Okay. Remember that. But the area of flow would be this one here. Okay. So basically, if you look at this subsection 3, it's actually the same as subsection 1. I don't mind if you want to combine them. I don't mind. Okay. I can just times 2. Okay. If you want, if you make sure it's the same dimension, right? The width are the same, then you can combine them. All right. It's faster that way. So once you have, you have your Q1, Q2, okay, and then Q3, then, okay, you can find, of course, each of the Q, you are substituting the various Manning roughness coefficient. So you add them up together, you have total Q already, okay. You have Q, this lah. Okay. Oh, in this case, all right, all Q are expressed in terms of Y1. Okay. So therefore, you have to solve for Y. Since you are solving it for the depth of uniform flow, once you have your Y1, you can, solve for your Y0. Okay. That's how it works lah. Okay. Determine all that. Okay. Q is given. All right. I didn't actually, when I explained this, I didn't even look at the question. I just go through explaining how you use the composite or the compound section formula. All right. I hope you are clear with it. Try it. Of course, if you have question, do leave your question in our chat, WhatsApp chat group. I'll get back to you next Sunday. We'll discuss it together if you don't understand any of this. Okay. Now, what activity I would like you to do for today? Because we are going to end our class early, right? Okay, discard this. Okay. I'm going to stop sharing this. Anyone know what I'm going to ask you to do for today?
No. I think quiz 2 because I saw
Quiz
error.
2.
Yes,
Yeah.
correct, correct. Some of you may have already received the notification. All right, through author. Yes, quiz 2. You have to do quiz 2. Now, of course, I'm giving much ample of time for you to do your quiz 2. Just a second, I'm going to share this. What I realized if when I look through your assignment number 2. Okay. When I look through your assignment number 2, there's actually no question on, to find the most efficient section for a triangular channel. So what I'm actually trying to do here, since I want you to learn about, how you come up with the best hydraulic triangular section. Now, here's the tip, the answer, you should find the side slope z equals to 1. Actually, this already give you the hint. It says the best triangular section is half of a square. This is a square. Of course, this would be, when it says half, that means sorry, when it says half, right, of course, your side slope, the slope would be 45 degree lah. Okay, only a square can make that. If you have um, if you have a rectangle but not a square, okay, you won't get 45 degree lah, basically. Okay, now what I want you to do is I want you to try to solve quiz number 2, and the due to submit this would be tonight, midnight. Is it okay? That means you have ample of time.
Okay,
Okay,
okay.
let's do
Okay,
it.
okay.
Midnight, okay. Saya nak you all cuba kena hantar melalui author sebelum 12:01 tengah malam. Okay. Maknanya last masa untuk hantar ialah tengah malam ni lah. Okay. Ada soalan tak setakat ni? Tak ada Kalau tak ada, remember once you have done with the quiz, you can proceed with assignment 1 sebab assignment 2. Because assignment 2, the due will be next Wednesday. I already mentioned that each assignment will have 1 week time to complete it. Okay, kalau tak ada, you can proceed with your quiz too. Alright, I'll end my class for today. I'll see you guys. Take care.
Thank you, Doctor.
You're
Thank you,
welcome.
Thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Jangan lupa isi attendance.
Thank you, Doctor.
Thank you, Doctor.
Alright, you're
Thank you, Doctor.
welcome. Yeah.
Thank you, Doctor.
Thank you, Doctor.
You're welcome.
Bye. Thank you, Doctor.
Bye bye. Fikri.